Okay, welcome to this example of finding the resultant force of two different 3D forces. So we're dealing with forces in space in 3 dimensions, and we have this sort of structure here that I've drawn. And you can imagine sort of a slab or some square piece of structure that, let's say, is hinged and supported on this line. And on the opposite end, at 2 points, it's supported by these 2 cables here and here. And these 2 cables connect at point A. Now, this is 3-dimensional, so I've drawn a lot of different diagrams that we'll get to in a second. But the question is stating that the tension in cable AB, which is this cable right here, is 500 newtons. And in AC, it's 432 newtons, so this cable right here. And with that information, we want to figure out what the resultant and the direction of the 2 forces at point A are. So you can kind of see that if we look at point A where the 2 cables are joined, there is a support here. And we want to find the resultant force at point A due to these 2 forces right here, these 2 tension forces right here. Now, if you look closely at A, you'll notice that A is in the XY plane only. In other words, it does not have a Z component, so it's just in this plane only. The Z coordinate for point A is 0, but A does have a X coordinate and a Y coordinate. So, what do we mean by resultant force? Well, if you remember from many of other examples in the past, we can calculate the resultant force by just summing all the forces that we want to find the resultant force for. So in this case, there's only 2 forces, TAB and TAC. So this resultant force is going to be TAB plus TAC, and T is just for tension. Now, before we get into sort of the calculations, I want to quickly review how we represent forces in 3-dimensional space. So just like we represented 2D forces with its X component and the Y component with, if you remember, unit vectors I and J, we can do the same thing for forces in 3D space. So a force can be represented by its scalar component multiplied by this thing called lambda. Now, lambda is a unit vector, and it's specific to the line of action of this 3D force. So in other words, just like the I unit vector represents the X direction of a component, and J represents the Y component, and K represents the Z component, this lambda vector right here represents the force along its line of action. And normally you'll see lambda written out like this, where you have the force scalar component times lambda, and lambda would be dx in the I plus dy in the j plus dz in the k direction, all divided by d. Now, what are these d's? Well, these d's are the components or the distances that we can use for the 3D vector, and we can figure out its total length, and then we can figure out its x, y, and z components, and we can use that information, and this right here is our unit vector lambda. So how does all of this help us? Well, if we know we can represent 3D forces like this, then what I think we should do to solve this problem, to figure out what this resultant force is we need to represent both TAB and TAC in this form. So in other words, we need to find the unit vector lambda for both TAB and TAC. Now remember, the unit vector lambda represents the direction or the orientation for that force's line of action. So if we're looking at, let's say, TAB, which is this line right here, so you have force TAB going along this line of action from point A to point B, we essentially need to know how this line AB is oriented in 3D space. And we can do so by selecting any 2 points on this line to get its orientation in space, because both of these points are going to have 3 coordinates each, and we can use both of those coordinates to figure out the orientation of that line. So for simplicity, I'm going to use point A and point B because we have these dimensions listed on this diagram. So that would make it easy to figure out where point A is located and where point B is located. So let's go ahead and start doing that for both TAB and TAC. So I'll go ahead and start with TAB first. So TAB is this 500 Newton tension force. And in order to figure out what our unit vector lambda is, we need these x, y, z, and this d component. So if you remember from previous videos, our dx was the distance from the ending point to the starting point. So because this is a tension force and it's pointed this way, we know the ending point is going to be point B and the starting is going to be point A. So for dx, the ending point at point B, the x-coordinate for that is just 0, and that is going to be minus the x-coordinate for point A. Now the x-coordinate, you can see, is going the opposite direction of the positive x-axis, which is going this way. So point A is 40 meters from y, from the origin. However, it's 40 meters in the negative x direction. So this is going to be the ending minus negative 40 meters. And what do you know about two negatives? They just cancel out. And so this is going to give us a positive value of 40 meters. Now for dy, we can do the same thing, our ending minus our starting y coordinates for both points B and A. So starting at B, you can see that, well, if the y-axis starts along this line, you can see that the y-coordinate for point B is also 0. And we need to subtract from that the y-coordinate for the starting point, which is point A. Now, point A, the y-coordinate is going to be this 45 meters in the positive direction. So this is going to be 0 minus 45 meters. And this, you'll notice, gives us a negative value for dy. Okay, so for dz, we can do the same thing. Our z-coordinate for point B minus our z-coordinate for point A. So for point B, our z-coordinate is going to be 50 meters because point B is located 50 meters along the z-axis from the origin right here. So that is going to be 50 meters, and then minus whatever z-coordinate for point A is. Well, remember from the start of the video, I said that point A is within the xy plane only. So it doesn't have a z-coordinate. Well, it does, but it is simply 0. So we can subtract 0 meters here, and we get a value of positive 15 meters. Okay, awesome. So we do have dx, dy, and dz for this tension of AB. Now we need to figure out what this d value is. Well, in order to calculate d, what we can do is we can take the square of all three of these components right here, add them together, and then take the square root. So in other words, this equation right here, dx squared plus dy squared plus dz squared, add those up and take the square root, and we get a value of d. And if we plug all those values in, we get something like this, where we have that 40 meters squared plus negative 45 squared plus 50 squared. And if we just plug this into our calculators, we get a value for d of about 78.2624 meters. Okay, awesome. So what does that allow us to do? Well, it allows us to use d, dz, dy, and dx. We can plug it into this formula for TAB, and we can determine the three different components for TAB. Now, the reason that's important is because we're going to do the same thing for TAC, and then we're going to add the like components for both of these 3D forces, and that's how we'll get our resultant force. Okay, so the next step is to take all of these values and plug it into this equation. Now we have unit vector lambda here. It's these values right here. For this F force, this is the scalar component of the force that we're looking at. So in our case, the scalar component for TAB is just going to be 500 newtons. So if I write TAB in the form of this, I'll do that down here somewhere. It's going to look something like this, where you have your scalar component, that's going to be 500, and then all the values we figured out for this lambda right here for TAB. Now, if I plug in those numbers, we get something like, well, TAB is 500 newtons, and then I can take all of those 4 values here and plug it in right here, and I get something like this. And then if I solve all this out and expand this equation into those 3 components, I get something like this. This right here, where TAB has components x, y, and z. So the x component is this 255.6 newtons in the positive I direction. Then you have 287.5 in the negative j direction. And then you have 319 newtons in the k direction. And so that sort of makes sense, because when we look at this TAB force, you can see that there's going to be an x component that's positive, there's going to be a y component that's negative, and then there's going to be another z component that is also positive. So that's a good way to kind of check the signs when you're working with these sorts of problems. So awesome, we figured out what TAB is, and it's this right here. But that only gives us part of the problem, right? We have TAB plus TAC. So we need to repeat this process for TAC. And I'll do that in a different color down here. I'll say TAB was equal to 432 newtons. This is a force vector. And we can apply the same methodology that we did for TAB. So we need to first figure out what dx, dy, and dz are for this force. And again, if we just look at the diagram, dx is going to be the distance from the starting point to the ending point of this line right here. So I'm going to pick 2 points along this line, A and C. And again, you can pick any 2 points along this line, but obviously, A and C are the simplest because we already have all of these dimensions for it. So again, your force vector is acting in this direction. So the ending point is going to be point C, and the starting is going to be point A. So what is dx? Well, it's the distance in the x direction for this force. And we know that if point A is starting here, or that vector, that force vector is starting at A and it's going this way, we know that the dx distance is going to be this distance right here all the way up to point C. So what is that distance? Well, it's this 40 meters plus 50 meters. So if you can kind of project point A down onto the x-axis right here, you can see that we're going to have to go 40 meters in the x direction, and then we'll have to go an additional 50 meters to get to this point C. So dx is going to be 90 meters, and that's going to be positive. So what about dy? Well, again, the ending point is C, and the starting point is A, and point C, you can see, is in the xz plane. And so dy, you can see, is going to be negative because the starting point is A and the ending point is C, and we always need to take the ending point minus the starting point. So the ending point for C, the y value is 0, and the y coordinate for point A is 45. So if we take 0 minus 45, we're going to get a value of negative 45 meters. Awesome. So lastly, for for dz, dz is going to be the same, where it's going to be the distance from point A to point C in the z direction. And that is just this distance right here, which is 50 meters. So this turns out to be 50 meters. Okay, now if we apply the same methodology that we did up here to figure out what D is for TAB, we can do the same thing for TAB. And if we just plugged in dx, dy, and dz into this equation right here, we would get a value of D equal to 112.3610 meters. Okay, so awesome. These 4 values are enough to figure out what this unit vector lambda is. And so if we represented TAB in that same form, we would get TAB is equal to the scalar quantity of TAB, in this case it's 432 newtons, times all of that unit vector lambda, just like that. Now, if we plugged in all of the numbers, that would look something like this, where TAB is 432 newtons, and then all those values for dx, dy, and dz to look something like this. So you have the 90 meters, negative 45, and 50 divided by our d value, which was 112. Now, if I simply expand this out, I'll get the three different components for TAB, and those are as follows. So we have a positive 346 newtons in the I direction, a negative 173 in the J direction, and 192 in the K direction. So great, we figured out the three components for both TAB and TAC, and sorry, it looks like I called TAC TAB, so that's my mistake. This, that should all be TAC, so let me change that real quick. Just like this. So, okay, now that we know the three different components for both of these forces, we can use this equation right here, R equals TAB plus TAC, to figure out what our resultant vector is going to be. So that's as easy as summing TAB right here plus TAC right here with like components. So resultant force is going to really be TAB plus TAC. Now, if I add those together, I get these three components right here. So 601.6 newtons in the I direction, and that was simply 346 plus 255, and then negative 460.5 in the J direction, and that was negative 173 plus negative 287, and then finally 511, which was 192 plus 319. I get this value right here. So that's great. We know the three different components for this resultant force. Now we need to figure out its magnitude. So what is R's magnitude? Well, that is just going to be the root sum square of these three components for R, and we can do that pretty easily. It would be 601.6 newtons squared plus negative 460.5 newtons squared plus 511.6 newtons squared, and then we can add those together and then take the square root. Now, if we do that, we get a value of 914.2 newtons. So that is the magnitude of this resultant vector for TAC plus TAB. Now, that's great. We figured out one part of the problem. The second part asked for the orientation via direction cosines for this problem. Now, if you remember from the last few lectures, we learned that direction cosines we could represent using cosine of theta x, theta y, and theta z. So the theta values are the direction angles, and then cosine of those theta values are the direction cosine. So the cosine of theta x is going to be Rx over R. So what is this Rx over R? Well, Rx is going to be the scalar quantity of the x component for this resultant vector. In this case, it's going to be 601.6. And R right, which is this 914.2 newtons. So in order to solve for theta x, I could take the cosine inverse on both sides, and I would get theta x is equal to cosine inverse of Rx over R. Well, what is R, or what is Rx? It's 601.6 newtons divided by R, which was 914.2 newtons. So if I solve this out, I get a direction angle for theta x to be about 48.8 degrees. Awesome. So that is theta x. Now for theta y and theta z, we can do something similar, where theta y is the inverse cosine of, in this case, ry over r. So ry was our negative 460.5 newtons, which was this value right here, divided by r, which was 914.2 newtons. If I solve this out, I get a theta y equal to 120.2 degrees. So there is theta y. Now, lastly, for theta z, that is going to be the cosine inverse of rz over r. Now RZ was 511.6 newtons, and then R, of course, was the same, 914.2 newtons. Now if I solve this out, I get a theta Z value to be about 55.9 degrees. And there you go. The direction cosines, or the direction angles, for this resultant force for these two forces, TAB and TAC.